William Phillips, welcome. We're here in Lindau at a meeting engaging young people with Nobel Laureates in conversation. And I wanted to start with your beginnings as a young scientist. You emphasize in your autobiography the importance of home life and school in making you the scientist you are. And I wondered if you'd like to talk about that a bit.
Well, it's interesting. My parents were not scientists. They really didn't have much to do with science as we would understand it. They were both social workers. But they encouraged my interests, and I think they would have encouraged my interests whatever they happened to be. And at a very early age, I can recall my interest turning towards science. They had given me a microscope as a present when I was quite young. I must have been something like 6 or so, probably because I was interested in the world around.
That is young. That is young.
And I can remember looking at all kinds of stuff with this microscope, and I can remember in those early days mixing together chemicals that I would find, not really chemicals, but sort of common household things that you might find around the house, and you mix orange juice with milk, and interesting things happen. And of course I was interested in lots of things, as I think all children are at that age, but it seems that at a quite early age I focused on science, and then not too long after that I focused on physics. And so I can remember by the time I was about 10 years old that I was thinking that physics was really interesting, and I would love to be able to do that sort of thing. Of course, at the age of 10 I had no idea what a physicist actually did on a day-to-day basis, but I was reading books about physics and about physicists, and it seemed really fascinating and fun to me.
And do you think those early experiences really shaped the way you've developed into a scientist?
Well, I think at the very least, the fact that my parents encouraged me to pursue these interests. I had a little laboratory in the basement, and I would burn things and blow things up, and they were always very tolerant of that. There were certainly times when, for example, I would blow out the fuses in the house, and they tolerated that kind of thing on my part. And I think that had they been very discouraging, that would have been a very different experience for me, and I might not have developed the same kind of passion that I did for science had they not been so encouraging. So I really have a lot to thank my parents for in that regard.
What about school? Was that?
Well, school, I would think I was very fortunate in that I went to a kind of experimental program when I was in 5th grade, if I'm remembering correctly. And I think it's the sort of program that's quite common today. You would probably, in the United States, they would call it gifted and talented class, or they might call it advanced placement or something like that, that they would put some children into advanced courses. But at the time it was considered quite experimental, and it allowed those kids to explore a different kind of learning than would have been the case if we'd just been following the ordinary curriculum. And we did advanced things in mathematics and in foreign language. I started to learn French at that age, which is something that has been very important to me in my professional life since then, because I spent time in France collaborating with Claude Cohen-Tanucci and Jean Dalibard and Christophe Salomon and people like that, Alain Aspect, who have all had a tremendous influence on my thinking as a physicist.
It's interesting that languages open doors that might not have been opened otherwise.
Yes, and it's one of the things that I often will tell people. They say, well, what should I study if I want to be a scientist? And I say, well, obviously you study science and math, but don't neglect the other things. Don't neglect to learn how to write a coherent English sentence. Don't neglect foreign languages, because this opens up doors of a personal nature. Of course, all scientists these days speak English, and you can communicate with them, but being able to speak a foreign language and live in a country opens up a different level of personal connection that I think can be very important in your life as a scientist.
Just exploring that theme a little, would it be too much to say that there are actually cultural differences in the way that people think about, for instance, physics that can only be accessed through different languages, or is physics just a universal language?
Well, that's a good question. I guess I don't know the answer to that. I think there are cultural differences in the way people approach problems. I'm not sure that those differences could only be accessed by foreign language, but I think it's clear that there is a French approach to doing science that is different from an American approach to doing science, at least among the French scientists that I know. Now, of course, people say these days the world is flat, meaning that things tend to even out across the world, and perhaps the differences are not as great as they once were. But I appreciate those differences very much, because the way I see the difference, what we might call the classic exaggerated version of the difference between the French approach and the American approach, is that the French would think of a problem, they would calculate everything that they could about that problem, figure out exactly what should happen, and then go into the lab and see that they had calculated. Whereas the Americans would think of a problem and say, wonder if I could do that in the lab. Go into the lab and see what happens.
More intuitive.
And right, and less theoretical, less, but obviously both approaches are extremely valuable. Having a mathematical approach to things and doing a calculation very carefully so that you understand exactly what you expect is very important, especially if you don't get what you expect. Whereas doing something without much expectation is also very good, because it doesn't prejudge your ideas about what you might see, and it also means that you may do things that you might not have otherwise done if you'd relied on a calculation to do it. You just go in and say, let's see what happens. And I think a lot of progress is made doing both kinds of things, and I'm really happy to have had the experience of working with other scientists who have those kinds of different approaches. But I want to emphasize, of course, that I've given you a kind of cartoon version of the difference between the French and the American approaches to science.
Understood. But you developed very much as an intuitive scientist, basically continuing the experiments in the basement.
Yeah,
idea.
I think that's right.
Yeah, and so can you in fact remember yourself changing your approach on finding that other people did things differently?
Well, I certainly found that I was able to take advantage of the more formal approach that other people took. I wouldn't say that I became more formal, but I became more appreciative of that kind of approach. I'm not sure I'm really capable of being as formal as some of my French colleagues, but I'm sure glad that they're around.
I wanted to turn to university and the experimental sort of burgeoning that goes on there, and you working in the lab and learning how to do research. Your thesis topic was a very precise one. It was measuring the magnetic moment of the proton in water.
Yeah.
And it's so precise that it's still the most precise measurement.
It is still the most precise measurement.
I suppose that to some that sounds like a rather kind of, well, but dare I say even dull thing to do. but obviously it's not.
Right.
What led you towards answering that sort of question?
Yeah. Well, I think that the reason why I ended up doing that was that as an undergraduate, I did some research involving magnetic resonance. And that research was not earth-shaking research. I published a few papers, but I got interested in the whole idea of magnetic resonance, and it was on my resume when I made applications to graduate school, and Dan Kleppner at MIT read my application. So, well, here's a guy who has a little bit of a background in magnetic resonance, and we're doing experiments in magnetic resonance here in the lab, so maybe he'd be interested. So he wrote me a note. That was the time before email. You know, people wrote letters, and I got this letter from Dan Kleppner, and I was really impressed that he would take the time to write to this poor kid in a backwater college. And I visited his group at MIT, and I was really impressed with the way that I saw the group interaction go, and I really liked the atmosphere in that group. And I decided that that's where I would go for graduate school, and I started working on problems that related to magnetic resonance, and I apprenticed with an older graduate student who taught me the ropes. And then when it came time to think about a thesis topic, Dan Kleppner suggested this thesis topic, and I was enthusiastic about doing it. Well, why was I so enthusiastic about getting the last decimal point? Well, the reason is that there are a number of fundamental constants in the world that are really basic to understanding how the world works. Now, the magnetic moment of the proton in water is not one of them, but you can use that to get some other constants that are really important. So the way it works is this. I want to know the fine structure constant. The fine structure constant is one of those really important constants. Basically, it tells you how strong electromagnetic forces are. And electromagnetic forces are basically everything that we experience in daily life except for gravity is due to electromagnetic forces. Everything we can see here, everything we can touch, the feelings that we have are about electromagnetic forces. It's just that in addition there's gravity, and that keeps us from floating away. So our lives are dominated entirely by electromagnetic forces. So understanding electromagnetic forces is really important, and a lot of the work of physics has been about understanding electromagnetic forces. And one of the most successful theories in physics is called quantum electrodynamics. It's basically a quantum theory of electromagnetism and the way in which quantum particles like atoms and electrons behave in the presence of electric and magnetic fields. And quantum electrodynamics can make really precise predictions about the behavior of certain kinds of objects. For example, it can make an extremely precise prediction about the magnetic moment of the electron. Now, so how do you figure out whether it's right? Well, you need to know what the fine structure constant is, because it predicts what the magnetic moment of the electron is using the value of the fine structure constant. Well, people had figured out how to measure the fine structure constant to an incredible level of accuracy and precision. And Hans Dehmelt got a Nobel Prize for that kind of work. But it was not possible to compare the theoretical prediction to the experimental measurement, because the experimental measurement was so good that we didn't have a good enough value of the fine structure constant. And by a roundabout means, you can determine what the fine structure constant is by measuring things like the magnetic moment of the proton in water, and other things as well. And the reason water comes in is that another part of the measurement is you wind a solenoid. You make a magnetic field with that solenoid. You measure the solenoid very carefully so you know where all the wires are. And then you put a hunk of water in the middle and you measure the precession frequency of the protons in the water. And that gives you a number, which doesn't do you any good because nobody cares about water. So what I did was I measured the magnetic moment of the proton in water relative to the electron. The electron matters. So it takes the water out. So you have one experiment with water, you have another experiment with water, the waters cancel out, and now you know what the precession frequency of electrons is in the magnetic field, and that can be used along with a few other constants to get the value of the fine structure constant. And so that's a really exciting thing, because you get to test one of the most precise theories that has ever been to a level that has never been tested to before, to try to find out, is this really right? Well, so far it looks pretty good. But we keep after this to try to test things to a higher and higher level of precision. That's one of the reasons why I'm at where I am. I work for the National Institute of Standards and Technology.
And I wanted to ask about that move, because it seems to follow on from the very fine, very precise measurement of your graduate work. And yet again, you will work at MIT, and people might, I suppose, have said, why go from MIT to the National Bureau of Standards, as it was then? Because it seems a bit prosaic, but obviously, again, not. No.
Yeah, so there's an interesting story that goes along with that. I didn't just do the thesis that you're talking about. My thesis was in 2 parts. And the reason was that when I was nearing the end of that measurement, I was thinking, well, that was wonderful. But the techniques that I used were very much techniques that had been in existence for a really long time. And in a sense, it was the culmination of that kind of work. At the same time, I was seeing that a lot of people were starting to do experiments with lasers, tunable lasers that could probe the structure and the behavior of atoms by changing the color of the light so you could excite certain energy levels in atoms. And it was only around that time, in the 1970s, early 1970s, that that was becoming possible, that you could choose what the color of the light coming out of the laser was. And I thought, wow, this is really a new way of doing atomic physics, something that hasn't been possible before. I'd really like to learn about that. And so I went to Dan Klepter and I said, I'd like to do an experiment involving lasers. And he said, sure, so let's think of another experiment. And so we thought of an experiment that, looking back, was pretty prosaic, but was new at the time and people were interested in it. It involved collisions of atoms that were laser excited. So I did that experiment, but the thing was that I learned about how to use lasers and how to make atomic beams and a lot of things that I hadn't been part of my experience doing the precision measurement. And so I did another experiment with that, and I wrote up both experiments together, completely unrelated one to the other, and the two of them together made my thesis. And at the time of the completion of my thesis defense, it was traditional for the thesis student to have a party to which all the people in the group were invited. And so I did that, and all these people were over at our apartment. And it's traditional for the thesis advisor to make a little speech about the thesis student. And Dan Klepter did that, and he said, it's a really good thing that you did that second experiment, because had you only done the first experiment, you'd probably end up at some place like the National Bureau of Standards. And 2 years later, that's where I was.
Was he disappointed?
I don't think so. And I'm sure he's not disappointed now. Because he was always interested in precision measurements. That made a large part of his life. And I think he was happy that one of his students was also following that route. And so I went there to do precision electrical measurements. But because I had spent time doing laser atomic physics, and because I had told them that I thought that was an important area of research and that I had some ideas that might be relevant to the mission of the Bureau of Standards, they gave me the leeway. I wouldn't say it was really enthusiastic, but they gave me the leeway to do, on the side, some experiments with lasers and atoms, while I was also doing precision electrical measurements.
Right.
And so, for the first several years, probably for the first, almost 10 years, I worked simultaneously on both electrical measurements and laser atom interactions. And the management at the Bureau of Standards was very, very helpful to me in getting that started. So I don't want to say that they were reluctantly allowing me to do it. They enthusiastically supported the work, but they always thought of the electrical measurements as being the main thing that I'd been hired to do. And I thought, well, this is nice, and who knows, it might lead to something. Well, it did.
Yeah. Was similar freedom being offered to colleagues? Was it an environment which basically said some of your time is your own to do what you want?
Yeah, I think that a lot of my colleagues were exploring new ideas with sort of spare time. A physicist doesn't have any spare time, but with stolen moments and borrowed equipment and various instruments scrounged in various ways, you could put something together. And I wasn't the only one doing this sort of thing. I seem to recall that the people who were working on scanning tunneling microscopy were sort of doing that a little bit off the record, and then that became a huge thing and exploded into one of the main activities. And of course, that's what happened with laser cooling. And I think it was very important that I was at the Bureau of Standards, because there were a lot of ideas that I was thinking about doing in atomic physics. And one of them was studying more scattering experiments, and one of them was pursuing Bose-Einstein condensation, which I'd worked a little bit on when I was at MIT. And one of them was laser cooling. And it just seemed obvious that since I was at the Bureau of Standards, that I should work on laser cooling because it had obvious applications to precision measurement. If I can make things colder, make the atoms go more slowly, I can obviously measure them better. So everybody recognized that that was a good thing, and Dave Wineland had already been working on that in Boulder and had started to have some really important success in laser cooling of ions. And then what I was trying to do was to do the same thing for neutral atoms in Gaithersburg. And
so Boulder was an offshoot of NIST as it was then? Or?
Boulder was an offshoot of NIST, but my thinking about laser cooling was an offshoot of what was going on in Boulder. Because the successes that I had were one of the things that inspired me to go into laser cooling of neutral atoms.
Okay. So if we turn to laser cooling for a while, so that was the work that you, together with Stephen Chu and Claude Cohen-Tanuji, were awarded the Nobel Prize in Physics in 1997 for.
Right.
You used a combination of laser light and a magnetic field to trap atoms, slow them down, effectively cooling them so that they could be studied. Why is it so important to be able to study slow-moving atoms in gas?
Right. Well, I already alluded to that, but let me just say a little bit about what you just said about the combination of lasers and magnetic fields and slowing and trapping, just to set that stage. One of the first things we did was to slow down a beam of atoms because we thought that was a good way to start. And to do that, we used a combination of a magnetic field and a laser. And the reason for doing that was that when you shine a laser in the opposite direction from an atomic beam, the atoms will absorb the light from the laser beam and slow down a little bit. But only the atoms that are going at exactly the right velocity will absorb the light, because the Doppler shift changes what frequency the light appears to have. And because of the motion, something moving toward a source of light will think that the frequency of the light is higher. And the faster it's going, the higher it looks.
And the frequency has to be exactly right for the photon absorption to take place.
Exactly. It has to be right within, say, 10 megahertz in order for the sodium atoms, which is what we first used, to absorb the light. And the velocity of the sodium atoms is so great and spread over such a wide range that it's seeing the shifts of the frequency of the laser to be well over a gigahertz. So more than 100 times the shift that would be tolerable. So what we did was we used a magnetic field that changes in space so as to compensate for the change in the Doppler shift. So we start with the magnetic field tuned in such a way that high velocity atoms will see the color of the light being the right color. We call that being resonant with the light. And then as the atoms slow down, then they see a different shift, they move into a different value of the magnetic field, and it all compensates. And then the atoms come out going very slowly. And then we developed a trap using just a magnetic field that could hold on to the atoms. And then we also developed other traps that could hold the atoms just using lasers. And other people, like Steve Chu, developed a trap that combined magnetic fields and lasers, along with Dave Pritchard, based on an idea by Jean Dalibard, just sort of showing how all these ideas come together from different people. So Jean Dalibard in Paris has this idea for a trap. Dave Pritchard looks at that idea and says, wow, I bet that would work. And he says to Steve Chu, I think we can do this in your lab. And so the thing finally happened. And then we saw that and we said, wow, that's a great idea. We're going to do that. And so we started using that. And so the way in which all these things have come together has been really important. Now, why are we interested? That's the question you asked.
Yeah, although I'm now going to come back to another question about competition in a second.
Okay, sure.
But let's deal with why first.
Okay, so why do you want to slow things down? Well, it's as simple as the fact that when things are moving fast, it's hard to measure them. So let me be a little bit more precise about what that means. Let's say I want to make an atomic clock, and that's exactly what we wanted to do, because I'm working for the National Bureau of Standards, now the National Institute of Standards and Technology. And one of our jobs is to measure time as well as we can, because that's our business, is measurement. We're supposed to provide the standards of measurement that anybody else who wants to measure things can use to measure things as well as is possible. It's our job to learn how to measure things as well as possible and to transfer that ability to measure to others. So time. we've got to make really good atomic clocks, we've got to broadcast what time it is, we have to broadcast signals that give out standard frequency, and we have to develop techniques that allow other people to make really good atomic clocks if they want to. So one of the big problems with atomic clocks is the atoms are the tickers for the clock, but the atoms are moving really fast. So there's several reasons why that's a problem. One is that they just don't stay around for very long. So if you want to measure how good the ticking frequency of one clock is compared to another, you want to compare them for a long time. You wouldn't go online and go to www.nist.gov and find out what time it was and synchronize your watch, and then come back a minute later to find out how fast or slow your watch is. You would come back after a week or a month to be able to find out whether your watch was fast or slow, assuming it's a decent watch. Well, you need a long time to make that measurement. Well, if the atoms are moving through your apparatus at a couple hundred meters per second, and your apparatus is only order of a meter long, you've got milliseconds to make the measurement. Yeah. So that's one problem. The other problem is what we talked about before, the Doppler effect. When something's moving, the frequency looks different. These atoms are moving really fast, almost the speed of sound.
So precise measurement is very difficult.
The speed of sound is about a millionth of the speed of light, and that ratio tells you how bad the effect is going to be. A part in 10 to the 6th, these clocks, we try to make them better than a part in 10 to the 14th. So people came up with all kinds of tricks to get rid of the Doppler effect, and the tiny bit that you couldn't get rid of is one of the limitations to how good the clocks were. Then another thing, Einstein taught us in 1905 that if something's moving, its time runs slower. So if the atoms are moving, time runs slower for those atoms. And that's not as big an effect as the Doppler effect. It's about a part in 10 to the 12. But when you're trying to do a part in 10 to the 14, a part in 10 to the 12 is horrible. And in order to fix that, there aren't any tricks. You have to measure what the velocities of the atoms are. You have to measure how many atoms have what velocity, and then correct for the fact that they've got different velocities and they're keeping different time because of the time dilation of Einstein. So all of these things together were reasons why the clocks weren't working as well as we would like them to work, and it all seemed to have to do with the motion. So we're thinking, and the people in Boulder are also thinking, let's do laser cooling, let's get the atoms so they're going really slowly, because of course cold means that the atoms are moving more slowly, so we'll be able to make better clocks. That was our original motivation, and is still one of the most important applications of laser cooling. Now, as it turned out, there were a lot of other applications of laser cooling that we didn't anticipate. But that was why I was doing it at the National Bureau of Standards.
All right, and it is now incorporated into atomic clocks, is it?
Absolutely. The United States, France, Germany, Great Britain all use laser-cooled atomic clocks, and a bunch of other countries, all use laser-cooled atomic clocks to keep time.
Is there a single timekeeping center?
Yes, there is. That's an interesting thing. I don't know that much about it, but there is an international organization called the Bureau International des Poids et Mesures, the International Bureau of Weights and Measures. I think of it as the International Bureau of Standards. And they collect information from atomic clock laboratories all over the world, compile it, and somehow take into account the fact that some of the clocks are better than others, and combine all of this information into a single time scale that is called Universal Coordinated Time, UTC. Now, what I don't know is there's different kinds of UTC, UTC1, UTC2, I don't remember, okay? But that is the official time for the world. Now, countries like the United States also keep their own time. So we keep sort of NIST time. And the Navy in the United States keeps their own time, so they keep Navy time. And, well, I mean, the differences are incredibly tiny, and in the end, everybody tries to coordinate to the international time. But, see, the international time, it's a funny thing. This may not even be true anymore, but at least traditionally, they would have all this information about time, and then they would publish tables that would tell you what time it was a month ago. So they would tell you what the corrections you would make to what, well, if you want to know what time it is now, you might want to keep your own time. Yeah. And that's what people do. So they keep their own time. Of course, obviously the people who are supplying this information to the BIPM are obviously keeping their own time. And so if you want to do something locally, then you work on your own time.
Sure,
but I'm not an expert in this.
But it's a fascinating world of sort of small variations and lots of people working to slightly different standards. Great. So back to back to when laser cooling was being developed. Several labs working on it at the same time. The picture you painted just now sounded like one of nice open collaboration. Is that how it was?
It was both open collaboration and fierce competition. So we were constantly in touch with each other about what was going on, but at the same time there was no mistake. Each of us wanted to be first. Mm-hmm. So I think that's ideal for the way science should be. I don't think that you should be secretive about what you're doing or about some of the great ideas that you have. I think you should be open. Like, take Jean Dalibard. Mm-hmm. So he has this wonderful idea for what became the magneto-optical trap. And he tells people about it. And, well, he could have said, well, gee, I've got a lab. I could go and try to do this thing in my lab, and I won't tell anybody until we've tried to do the experiment. But he didn't do that. He told people about it. People said, well, that's a great idea, and did it. And everybody knows, at least I hope everybody knows, that it was Jean's idea. He didn't even write a paper about it. But there's a notation in the paper that was written about it saying this idea came from Jean Dalibard. And well,
the principle being there isn't time to do everything, but one should share one's ideas, do the things one can do quickly.
That's my opinion, that you should share your ideas. Now, I know that there are people who are reluctant to do that, who think, well, if I've got a good idea, I don't want to have somebody else take it and get the credit for it. But I really think that both an individual scientist and science as a whole are both better off if we're completely open. So let's take something like that idea. Well, it was widely enough known that Jean Dalibard came up with the idea that everybody gives him credit. Now, if he'd kept the idea secret and then somebody else had come up with the idea, then they'd get the credit both for the idea and for the experiment if they succeeded in doing the experiment. He didn't do the experiment, but he came up with the idea, and everybody knows that. So that works to his benefit compared to keeping it secret and maybe having somebody else do it. And it obviously worked to the benefit of science because probably the experiment was done more quickly. Because the reason that Dave Pritchard didn't do it was he didn't have the right equipment. So he goes to Steve Chu and says, you know, how about if we do this together? And Steve Chu hadn't thought of that, and so together it all works, and then the world has this wonderful new tool, which was a really powerful tool. It transformed laser cooling. So it was really great for science, and I think it was great for the individuals who were involved.
Do you think is it possible to say whether it's getting more or less difficult to take that approach in the current environment?
Yeah, well, that's a good question. I don't know. I hope not.
Okay, that's a good answer. When you choose people to come and work with you, I imagine that you need a special set of skills to work at somewhere like NIST. You need a kind of inquisitiveness about nature and also the extraordinary precision of being able to work with the systems you work with. What do you look for in the people you employ?
Yeah, well, I'm not sure that I am the best interviewer of people to determine whether they're really good. But fortunately, I have a bunch of colleagues, and when somebody comes to interview with us, everybody looks at them and sits down with them and talks with them and gets an impression. And then we get together and we think, well, is this the kind of person we want to have working with us? So it's not just my own judgment. But I think that the kinds of things that I look for are somebody who is indeed inquisitive, somebody who asks a lot of questions, somebody who thinks clearly about physics. So usually somebody comes to visit us to interview for a job. We have them give a talk, and during the talk we ask questions. And the way in which the person responds to the questions tells us a lot about how clearly they understand things. Now, I'm not usually asking questions just to probe to find out whether people understand things. Usually I'm asking questions because I want to understand what they're doing. But usually it'll come out whether they understand things very well or whether they're a little bit confused about things as well. And that goes into our thinking about whether somebody is the right kind of person for us. We aren't so much looking for someone with a specific set of skills. We have had some of our best people have been people who came from completely different areas of physics. So for example, one of my young colleagues is named Ian Spielman, and he came to us from a background of condensed matter physics. He didn't use lasers, and he didn't have atomic beams and things like that, and didn't know anything about laser cooling. Well, he read about it, but he did condensed matter physics, and he thought, well, it'd be interesting to learn something about a different field. And he came very well recommended. It was clear when he visited that he was really smart, and so we hired him on as a postdoc. We were so impressed with him that when he finished the postdoc, we offered him a permanent job. And he brings something to our group that other people don't, namely a really good solid background in condensed matter physics, because the rest of us, well, most of the rest of us, I should say, were atomic physicists. Actually, we've got another guy who came from a background of liquid helium research. Very different from the kind of condensed matter that Ian Spielman did. Trey Porto did liquid helium work at Cornell, and then he went and did a postdoc with Dave Pritchard at MIT doing ion trapping. And then he came to NIST to do other kinds of things, and we picked him up to become a laser cooler. And so this diversity of backgrounds is something that we think is very good for us. And so we have 3 other guys who are basically atomic and laser physicists. And so together we span a wider range of backgrounds and specific knowledge.
Just with inquisitiveness in common, yes.
Yes. Well, I don't think that anybody goes into physics without the idea that they want to learn about the way the world works. But there's different levels and different styles of inquisitiveness. And the kind of person I like is somebody who is asking questions about a lot of different things. Just, never at peace.
Yeah. And sort of flipping it around, what do you try and teach people who come to work with you?
Yeah, well, that's a good question. First of all, I should say that most of the people who come to us come as postdocs. We have a few graduate students, and I hope that in the future we will have more graduate students. But most of the people who come to us are postdocs. So while I think that your duty as an advisor to a graduate student is to teach them how to become an independent researcher, I think your duty to a postdoc is to give them the freedom and the tools to make their own way. So we treat postdocs differently from the way we treat graduate students. For a graduate student, we want to make sure that they've learned all this stuff. Of course, the postdoc may have to learn some new stuff too, but at that stage you figure they'll pick it up, they'll ask a question if they need something, they'll read an article, you'll spend some time discussing something. But I don't go out of my way to teach a postdoc the things that they need to know. I figure they'll figure out what they need to know, and they'll ask or they'll read about it or whatever. What I want to make sure is that they've got the resources, the infrastructure, the tools to carry out some new ideas. And so what I'm expecting a postdoc to do is to think about some new directions, to be starting to set the directions that the experiments are going. Typically, as a graduate student, you start by doing something that your thesis advisor says is going to be an exciting idea. That's certainly what I did as a graduate student. And as it progresses, you start to come up with your own ideas and the direction in which you go to actually realize the problem that you have been set to come to a good conclusion is very often your own doing.
Should be your own path, your own invention, yeah.
And when you're a postdoc, what I expect of a postdoc is to set the directions. Now, they may not do that at the beginning, but that's what I'm expecting, is that they're going to set the direction. So at the beginning, we may suggest some ideas, but what I'm expecting is that postdoc to come in and say, let me tell you what happened in the lab, and let me tell you what I think we ought to be doing. Or, you know, in the shower this morning, I was thinking, maybe we should do this. That's what I'm expecting from a postdoc. And so I don't see myself so much as teaching them as being able to provide the right environment, and obviously providing advice and guidance along the way, but basically having them start to be the leaders.
Mm-hmm. I'd like to change direction a little, if I may, and if it's okay, talk about your faith, because you are perhaps a little unusual among Nobel laureates in physics that you freely talk about your faith. And
well, only when people ask.
quite a lot of laureates freely talk about their sort of disdain for irrationality. So it's the flip side.
Yeah.
So how does that connect with your work, if it does?
Well, first of all, let me say that I don't think I'm in any way unique in being a person of faith and being a Nobel laureate in physics. Charlie Towns is a person of very strong faith. Art Shallow, you know, any number of people that we could talk about, and even some people might think even less likely would be Nobel laureates in biological fields who've wanted for medicine and physiology or some biochemical things, because often biologists feel most under attack from what you might say creationist religious thinking or something like that. But in fact, I know plenty of biologists, Nobel laureates for that matter, who are people of faith. So it's not that unusual. I think it's perhaps simply that when we get together as physicists, it's not the thing we most naturally talk about. Now, so how does it work? You're asking. How does it work? My faith and my science.
I think I'm asking. I think I'm more asking, what part does faith play in your work?
Okay, so there's a couple of things that I would say that faith plays. I believe that God has given us a magnificent universe. And I think that one of the reasons why it is so magnificent and beautiful is that it's a kind of a gift to us. And so I think that finding out about the beauty of the universe, which is one of the things that I would claim physicists are doing, is discovering the beauty of the universe. And one of the great things about physics is it seems that the more we study it, the more beautiful it gets. So to me, that sort of thing is a holy calling, because we are responding to a gift from God. So that's part of the way I see faith relating to what I do as a scientist. The other thing is, and I think this should be true for every person of faith, that you should pursue what you do in a way that is consistent with the principles of your faith. Mm-hmm. Now, sadly, a lot of people who are people of faith, or at least are trying to be people of faith, fail to carry out their profession in a way that is fully consistent, including myself. I mean, we all fall short of those principles. I mean, the principles of the Christian faith are pretty difficult to live.
Yes, indeed.
And so I do my best. And so I try to do, I think, the same kinds of things we were talking about before. Be open with colleagues, not try to be secretive, and certainly not to try to do things that would impede the success of colleagues, even when they're your strong competitors. So simple principles of honesty and fairness are the kinds of things that I think every religious faith would say are the things that you should be doing with your life. And so as a person of faith, I believe that a scientist who is a person of faith has an obligation to work in that way. And so while I also believe that that's the best way to work to have success in science, it's also the right way to work according to my my religious principles.
And it's difficult, of course.
It's always difficult to live up to a high standard, but you know, in a sense, I suppose that's why the standards are high, so that you have something to aspire to.
Yes, thank you. That was very clear indeed. I think that on that note, we've covered a lot of ground, and I'd like to say thank you very much indeed.
Wonderful.
Enjoy the rest of the meeting.
Thank you very much.
Pleasure to talk to you.
It's been a pleasure.
Thank you.